Welcome back to the channel. It's your girls again, and we're ready to show you what we did this week for physics. Yeah.
Okay, so on Tuesday, the first experiment that we participated in was creating a sundial. A sundial measures how the sun's shadow changes angles over time. The change allows us to see the change in time. So to do this, we're going to insert some pictures, but first I'll just show you this little thing. So our first measurement, this is our mock drop of our shadows. Our first measurement of the shadow was taken at 12:26, and then our next one is taken at 12:50. So you can see based off this that the angle has changed.
In lab this week, we talked about different ways to measure time. For this experiment, we used a spring pendulum to measure time. So we put a spring on this. We used a spring and used two different weights. The first weight we used was 20 grams. We did a total of 10 laps, and for lap 1, we found that each time the spring bounced up and down, it was 0.51 seconds. Lap 2 was 0.51 seconds, as well as lap 3. Lap 4 was 56 seconds. Lap 5 and 6 were both 51 seconds. Lap 7 was 53 seconds. Lap 8 and 9 were 59, and lap 10 was 53. The next weight we used was 100 grams. We found that the first lap was 1.6 seconds. Lap 2 was 1.11 seconds. Lap 3 was 1.5 seconds. 1.15 seconds. Lap 4 was 1.16 seconds. Lap 5 was 1.18. Lap 6 was 1.03 seconds. Lap 7 was 1.01 seconds. Lap 8 was 1.11, as well as lap 9, and lap 10 was 1.18 seconds. For the 20-gram weight, we found that the average of each bounce was 0.54 seconds. With the 100 grams, the average was 1.10 seconds. And then here is our histograms of the data of the average that we got for each weight.
The next thing we talked about in lab was swing pendulums. So for this lab, we decided to use a tool already given to us, already made for us, and that was a meter stick that had 1 kilogram on the end. So we'll insert a clip of how the pendulum would go back and forth like this and not teeter-totter, but swing, because it's a swing pendulum. We measured it 10 times, and so for the first time we got 1.88 seconds. For the second time we got 1.90 seconds, 1.91 seconds, 2.03 seconds, 1.86 seconds, 1.95 seconds, 2 seconds exactly, not exactly, but 1.9 seconds, 1.93 seconds, and then finally 1.91 seconds. From all of this, we got that the average swing time was about 1.93 seconds. And doing both of these pendulums, we were able to decide that the same time that it took for it to either bounce or swing was roughly the same exact time every single time. So they were a very accurate way to measure compared to the sundial or what we'll talk about next, which is the drip clock.
Okay, so then the next one that we did, and the final one that we did, is the drip clock, which what we did is we went to the back of the room and there's a sink back there. We had the water going just enough so it would drip multiple times, and we would pretty much time the distance between each drop. So we did this 10 times, and for the first one we got 2.56 seconds. The second one was 2.88. The third one was 2.98. The fourth one was 2.95. The fifth one was 3.01. The sixth one was 3.05. The seventh one was 2.98. The eighth one was 3.11. The ninth one was 2.98. And the 10th one was exactly 2 seconds. So our average after that we got is 2.85 seconds. So the drip clock was the easiest one to build because everyone has access to it. So it was something super easy that all the groups could do.
As a group, we decided that the swing pendulum was probably the most accurate out of all of these forms of measurements. The swing was the most accurate, and then the spring was the second most accurate.
So today in lab we learned about the measurement of walking velocity, the average acceleration, and the measure of the speed of sound. So to start with that, we started with the walking velocity, and we each walked from the front to the back of the classroom, which is 9.5 meters. 9.5 meters. So we all did that and we timed it on our phones individually. So Skylar got 6.76. The time that I walked was 8.68, Addie's was 8.92, and Taylor's was 8.37. So after we found that, we divided them by 9.5, each of them individually, which gave us the answer, the velocity of us walking. And so Skylar's total was 1.405, mine was 1.094, Addie's was 1.065, and Taylor's was 1.135.
So to find out how large or smaller velocities were, we took the distance from wall to wall, which was the 9.5 that Allie mentioned, and then we divided that by how long it took us to walk that. So that's how we found all of our velocities. Next, we're going to talk about our accelerations individually because we all got different times. So when we do our accelerations, it's a little bit different than finding the velocity. So to find acceleration, we take the change in velocity divided by the change in time. So from this, it would essentially look like our velocity divided by time. So when I did that, I got 0.135 meters per second.
I got 1.07 meters per second.
I had 2.07 meters per second.
I had 1.03 meters per second.
To end our lab, we took a little walk to the main campus green area. And we did this to measure sound, the speed of sound, not just sound. So we set up this experiment by taking what seemed to be a slapstick, something that goes boom, like that, and standing face to face, I guess, with beard cheer. And so we slapped the slapstick, and then we listened for an echo back. And so when we did that, we also made sure to open the voice memos app so that we could get an accurate representation of when the echo came back at us. And we guesstimated, from what we could do at least, that the echo took at least 0.5 seconds to come back to us. So we took this 0.5 seconds and put it under 214 meters, which was the distance from us to beard chair and back, because we couldn't just do 2 beard chair. And so when we did the 214 divided by 0.5, we got an answer of 428 meters per second, which is pretty close to the real speed of sound, which is around 330 meters per second. So it's in the general ballpark area, so not too bad.
To conclude our labs for this week, we found that learning the measurements of velocity and time, acceleration, those are all important things that we could in the future teach kids in our classroom. The measure of time and speed are important and also easy measurements to adapt to different grade levels.
Velocity is also one of the starting grounds for learning physics, and it's one of the many fundamental mathematical equations that you should start off knowing so that you can advance your physics knowledge. And so understanding how to do this is not only beneficial towards us, but also towards our future children, which will at some point in their lives have to understand what velocity, acceleration, and time can all mean together.
We also found throughout all of these experiments that all of these experiments are fun and creative ways to introduce these new ideas to your students, and they're also easy, accessible materials that any classroom can have.
I think learning about clocks and velocity is really important for especially upper elementary as they transition to go into middle school and high school, because then they're going to be going into deeper studies about it. So I think this is a good way to introduce the topic to them so they can get an idea of it.
And then you explain.
Thank you guys.
Thanks for watching.
Peace out. Like and subscribe. Hit that. Yep.
See you next week.
Make my subscriber count to 4. Thanks.